This is VLSI data conversion circuits, lecture 49. In the last class we saw various aspects that govern the timing of a flash A to D converter and how one would arrange the times of the sample and hold and the preamp and the latch in order to be able to maximize the time available for each particular sub block. And we also saw a case study where all these concepts have been put together to realize a flash converter, and you saw that the preamp is pretty much the same kind that we discussed in class, the latch is the same that we discussed in class, and so on. The only minor trick, if you will, was that one could actually remove a comparator from the array and not worry about it too much, because one could use the bubble correction logic to mask the random decision that the comparator gives. This way one finds that one can continue to auto zero all the comparators in the background without affecting the conversion SNR too much, okay, because only when the comparator which is close to the ideal thermometer transition point from all ones to all zeros, that is when pulling a comparator out of the array makes a difference, and we saw by calculation that it is only about a dB or a dB and a half, and especially when you duty cycle this over a long period of time, the effective loss in SNR is a very small number. The other trick was that any static distortion in the sample and hold can be corrected by simply pre-distorting the references in the same manner, and this way you get cancellation of the distortion, thereby improving the or increasing the potential swing that is possible. And once you are able to efficiently utilize the maximum peak to peak differential swing, you are always, you are in a position where you can, within quotes, increase the random offset that you can tolerate, which finally boils down to power reduction, okay. And this is a general principle in analog. You always want to operate with signal swings which are as large as possible. Of course, trying to make signal swings very large will fundamentally mean that you have to worry about distortion, right. So we have seen this in many contexts. I do not know if you remember, but in the very beginning of this course we were talking about a sampling switch and a capacitor, and we said that, hey, the distortion in the sampled and held waveform is proportional to signal amplitude square, like it always is, and then one can take the easy way out and say I am going to use a bad switch, right, but I am going to reduce or restrict my signal swing. This is not a particularly good idea, as we saw in the analysis, that if you reduce the signal swing, the kT by C noise will increase. If the kT by C noise increases, it means that you now have to use a larger capacitor in order to maintain the same signal to thermal noise ratio, which means that the displacement current through the capacitor is now increased and you are pretty much back at square 1, you understand. So this is a general principle. If you try and operate with too small a signal level, you will find that you are limited by, your SNR is now determined by thermal noise, okay, and in order to maintain that SNR you have to increase or scale up the impedances or scale down the impedances such that the kT by C component becomes sufficiently small, and this will basically mean that you are paralleling many identical circuits together, which means that you have a larger power dissipation. So always you pay a penalty for working with small swings. So you ought to try and ensure that your signal swings are as large as possible, and the challenge there then becomes that you need to design amplifiers or circuit blocks which are capable of handling large signals without distorting too much. Okay. All right. So, the last couple of points I wish to make with regard to the flash converter architecture is the following. And we got into this flash converter simply because we were discussing a delta sigma, and the quantizer in the delta sigma loop needed to be as fast as possible, and the fastest way of making a decision is the flash converter. So, we went and got into the details and the nitty gritty of a flash, but a flash converter, as you can imagine, is also used in other situations where latency becomes a paramount issue, and where you cannot afford the delay that is characteristic of other A to D converter architectures. Okay. So, coming back, taking a step backwards, and then after the discussion on the flash architecture, a couple of things that pertain to flash converters, especially with regard to a delta sigma loop. One thing that we all know now is that ADC non-idealities are noise shaped in a delta sigma loop, right. On the other hand, D2A converter non-idealities are definitely not noise shaped, because those errors appear as if they are added in along with the input. Okay. So, this means that you can get somewhat sloppy on the A to D converter design. Okay. And so, there is also another aspect that usually the quantizer resolution in a delta sigma modulator is restricted to about 4 bits. There is no hard and fast rule or restriction, but 4 bits seems to be a good trade off between complexity of implementation on one side and the benefits of using a multi-bit quantizer on the other. So, it is a good balance between the two. So, you will find a lot of papers in the literature where the quantizer resolution is fixed at 4 bits. Okay. So, this means that some things which would not be practical in a higher resolution flash ADC, a standalone flash ADC typically would be a 6 to 8 bit converter. A 6 bit resolution is somehow very popular for a whole bunch of flash converters. Less than that is too little resolution, more than that is within quotes too difficult to do. So, in a lot of systems a 6 bit resolution is apparently enough, in which case you go for a 6 bit flash converter if latency is a problem. A classic case in point is the disk drive read channel system that I was describing to you way earlier in this course. Okay. So, one common aspect of these 4 bit flash converters used in delta sigma modulators is the following. So, let us discuss comparator offsets. So, if the comparator offset in a flash converter is large, what do you think will happen? You will obviously the thresholds are shifted from their ideal positions. So, you will have DNL and INL issues, okay. And if the threshold shifts too much, you can have a non monotonicity in in the flash sometimes you can even have a missing code, okay, and so on. So, a DNL and INL problem is usually not an issue in a delta sigma loop, simply because nonlinearity only causes the quantization noise flow to rise, okay. I mean, so if you take a standalone quantizer, the ideal spectral density is delta square by 12 divided by Fs by 2, that is the noise spectral density of the quantization noise. Now, if the thresholds are moving around or have moved around from their ideal positions, then this noise floor will increase, accompanied probably by also distortion, harmonics and so on. However, this increased noise flow is not really a concern, because all this is getting shaped out of the signal band, okay. Now, the only thing that one needs to worry about typically is to make sure that the characteristic does not become non-monotonic, okay, and which can become a problem when the converter is embedded in a feedback loop. So, what one normally does is you have the comparator array, you have bubble correction, plus transition detect, plus decoder, okay. When this flash is embedded inside a loop, for example like this, okay. Now, couple of things, the sampling action itself, where do you think one can realize the sampling action? I mean, if the number of comparators, what is the purpose of having a sample and hold in a flash converter?
If skew comes,
if the clocks are skewed, then you end up with poor dynamic performance, okay, and therefore you have if you have a sample and hold, that problem is avoided, okay. In a delta sigma loop, there are two things. One, the flash is a very much smaller flash, correct. A 4-bit flash is 4 times smaller than a 6-bit flash, for example, and therefore the speeds so the clock skews involved will be much smaller, and to begin with, you in a delta sigma loop you need to be worried about the entire loop as such. It is not just the flash alone. So, just because you can make a flash work at a very high speed does not mean that you will be able to put that flash inside a delta sigma loop and make the whole delta sigma loop run at the same clock speed as the flash, right, which explains why you see, if you look at the highest speeds of flash converters reported in the literature in a given technology, you will find that the highest speed delta sigma converters reported in the same technology are much slower, right. I mean, if it was very straightforward to take the same flash and put it inside a sigma delta loop and make the whole loop run at a very high speed, somebody or the other would have done it, okay. But the problem with these very high speed flash converters is that the latency can be a significant fraction of the clock period, which means that the moment you try and embed this inside a delta sigma loop, you will have all sorts of problems associated with excess loop delay. Okay. So, for example, if the latency of the flash is close to one full clock cycle, then the if you did not do anything, of course the loop would be unstable, right. You have to really compensate for a whole cycle of excess loop delay. Okay. And of course, if the latency is greater than a clock cycle, then at least what we have discussed in class does not work, is not it, because that ensures that you need the data before. I mean, how would you solve the problem of excess delay in a continuous time delta sigma modulator? You need a direct path around the quantizer, right, where that direct path provides the first sample of the loop filter, the so called loop filter impulse response. The loop filter is unable to provide anything simply because its excitation is coming so late, alright. Now, if the delay or the latency of the flash itself is more than one clock cycle, then the direct part does not help either, because its output is the output has not been generated even after the end of one clock cycle, you understand. So, these kinds of problems make it difficult to clock a delta sigma loop as fast as one would be able to clock a flash converter by itself. So, flash ADC working in inside a delta sigma loop will have, first of all, lot fewer clock skew problems. Not only that, the speed with which the converter is running itself will be slower than would be possible for a pure flash, where latency is not as big a concern as it is for a delta sigma loop, correct. This means that you probably do not need a dedicated sample and hold to sample the output of the loop filter and hold it before going into the comparator array. One can directly drive the comparator array using the implicit sampling in the latches itself, right. The comparator array, each slice can be considered of as having a preamp and a latch. So, and the latch is inherently sampling the output of the preamp and making a decision. So, there is inherently sampling happening inside the latch. So, one could say, hey, first of all I am running at much lower speed and clock skew is not an issue. So, I can simplify my life by getting rid of the sample and hold. Okay. That is one simplification that is often made, right. The next thing is to try and simplify the comparator itself. The comparator is basically, we have seen it to be a preamp and a latch. The goal of the preamp is to reduce the input effort offset of the latch. Okay. So, there have been realizations where, in an attempt to simplify the comparator, one just does not bother with a preamp at all and simply uses the latch. Again, I would like to bring to your attention that several possibilities exist for the latch. It is not necessary So, this is LC, latch reset, latch enable, okay, and then you hold this on some other delayed clock. Okay. So, this way the sampling instant is the falling edge of LC, okay. And the data is available at the rising edge of at the falling edge of LED, as we discussed before. Yeah, that's a good point. This differential latch can only distinguish if these two inputs V in P and V in M, if they are if one is greater than the other or not. Okay. One still needs to be able to subtract references, and one way of subtracting references is to say, in principle what one needs to do is to apply, if one had a battery all right. This in principle would then detect this, whether VIP minus Vref P is greater or VIM minus Vref M is greater, and this is equivalent to comparing VIP minus VIM minus Vref P minus Vref M. Does it make sense? Okay, now can you suggest how one can subtract references from here? How can one implement these batteries? So, the usual trick of having a capacitor. One important observation to make is that when are these batteries not needed? Or when are these capacitors needed?
These off.
You need these batteries only when LC is
Off.
is high, correct? When LC is not needed, or when LC is low, the latch is regenerating. So, at that time these batteries are not needed, which means that is a good time to charge the capacitors, which will invariably lose charge otherwise because of all the switches connected to them. So, conceptually one could do this. So, if this was for instance VIP, VIM, Vref P and Vref M, when LC bar is high, okay, what happens? When LC bar is high, these capacitors are charged to, the capacitor on top is charged to Vref P minus VCM and the lower capacitor is charged to Vref M minus VCM. Okay. When LC goes high, these capacitors are placed in series like this, okay, and the voltage here is, if there is no parasitic capacitance at those nodes, then the voltage across the capacitor C, let me call this CB, the voltage across the capacitor CB does not change at all, and the potential stored on the parasitic capacitance at these nodes will be VIP minus VIM minus Vref P minus Vref M. Okay. In your assignment, I have given you another flavor of the latch, where again the input is subtracted using coupling capacitors, using a somewhat similar switching arrangement. Okay. Note, however, that we are still stuck with the offset due to the latch, okay. And if the offset becomes very large, then you can end up with errors in the with very large errors in the thresholds. But since the number of comparators is very few, for example, a 4-bit flash requires only 15 comparators, one does not really have to implement bubble correction logic and the transition detect and a decoder and such. Okay. One other way of generating the digital output sequence as a function of the thermometer code that appears at the outputs of the comparator is to simply add up the number of okay. So, now if there is a bubble, if you if you add up the number of ones appearing at the output of the comparator array, do you think it matters? For example, ideally let us say this should have been the thermometer code, but let us say for argument's sake that this shows a 0. If you normally took this thermometer code without bubble correction logic to a transition detector and then through the decoder, you would get a completely erroneous value, simply because the transition detector, which is accustomed to only seeing a single 1-0 transition, now sees 2 1-0 transitions and therefore is confused. Okay. Now, what if you simply add up the number of ones in the thermometer code, what will you get? If you just simply count the number of ones in the thermometer code,
Only one less.
you will only make a very small, you will make a 1 LSB error, correct. So, this way addition of the number of ones in the thermometer code gives you something which is within quotes insensitive to bubbles without actually having any bubble correction logic. However, adding up in a regular flash where the resolution is not as low as 4 bits, for example, a 6-bit flash converter, adding up all the ones in the thermometer code would mean adding up 63 numbers, right, which means a whole bunch of adders and that sort of thing, which makes it not a very practical idea for large resolutions. For small resolutions, however, if you have only 15 comparators, finding the number of ones in the thermometer code is not a very expensive task from a viewpoint of hardware, right. How do you suggest we add up the number of ones? Pardon? Yeah, I mean the easiest way of doing this is to combine, add up neighboring bits and then add up successive neighbors and so on. So, you get some kind of tree structure, right, and where the depth of this tree is dependent on log n, where n is the number of numbers you wish to add. I think this is called what is called a Wallace tree adder, right. Okay. So, this is something which is also done in flash converters, especially those used in a delta sigma loop. Okay. Now, this addition of these ones to give you the binary code, this addition does not have to be done within the loop, you understand. So, the output of the sigma delta loop can be simply the thermometer code that comes out of the comparator array, as long as the DAC is happy to receive the thermometer code, all right. The thermometer to binary logic can be done outside the loop, you understand, and therefore, the latency involved in combining all these ones etc. is not a part of the loop at all and does not contribute to excess loop delay, right. But it is important that the binary the DAC be able to accept a thermometer code. It turns out that this is actually a blessing in disguise, because most DACs, right, will be much happier with a thermometer code rather than a binary code, and so this works out quite nicely. So, the DAC is driven by thermometer code, and the thermometer to binary conversion is done outside the loop. Does it make sense? All right. So, let me summarize. This will make this immune to bubbles. Can you comment on the solution and its what this would do if the offsets in the latches were very large? Pardon? Think carefully. Let us say the offsets in the comparators were very large. No, that is not what I am asking you. I am asking you, can you comment on, I mean in a regular flash converter where we have the thermometer code and the usual bubble correction logic, etc. If there are big offsets in the latches, right, offsets larger than an LSB for example, can you comment on what happens to the output code of the flash? Let us say you had the ideal comparator levels thresholds were these, and by some quirk of fate this threshold remained like this threshold remained like this, and this threshold became like this. Then what do you think will happen if the input was here for example? What thermometer code would you get ideally? 1 1 0 is what you would get. Now what would you get? You will get 0, you will get 1, you will get 1. Now what happens if the input happens to be here? Actually I should have got 1 0 0, now I will get 1 1 0, okay. So this basically I mean you can see that this causes a fair amount of error, right, and I mean this is a rather, let me take a even more pathological example. Let us say this threshold moved here and this threshold moved there, okay. Then what will you get if the input was here? Ideally you should have got 1 0 0, and now what will you get? 0 1 0, okay. So if you did not have bubble correction logic, you will find that this gives you a whole lot of pathological errors, alright. I mean assuming everything below is okay, this is what you would get, right. Now if comparator thresholds, now if you add up the number of ones in the thermometer code, the fact that comparator thresholds move does not really it does not matter. Is that clear?
The total number of ones comes.
Do you understand? See, in a regular flash array, the location of the threshold does matter, because the position of a comparator in the array matters, in the sense that if I physically move a comparator down, right, I have the array, if I interchange the position of two comparators while having the same references to them, giving the same references to them, what will happen to the output code? It will be in grievous error, because the logic following it does not know that the positions of the comparators have changed. However, if you add the number of ones in the thermometer code, right, you can move the comparators around without affecting the output code, because as far as the final output of the A to D converter is concerned, every comparator output contributes in the same way, because it is symmetric from the output of the path from the output of any comparator to the final output is logically the same. You understand, because all that is happening is that if the output of a particular comparator is 1, it contributes 1 to the final code, but that is not the case in a conventional flash array, where you do this transition detect from the all ones to the all zeros. Okay. There the outputs of several comparators, okay, I mean the ones which are near the transition point are the ones which really matter, okay, and therefore the position with which I mean the position of a particular comparator does affect the output code. Is this clear? If I take I mean if I, in other words, so let us say all these and then this goes to the digital backend conventionally. All right. If I now swap these two wires, for example, what do you think will happen? The output code will be in error, isn't it? Whereas instead of having the conventional digital backend, if I just simply added the number of ones in the thermometer, what would happen? There will be no change in the output code, correct. Now, changing the position of these comparators can be thought of as change in offset, you understand. So, in other words, you were trying to realize comparators with these thresholds, due to offsets I got this, let us for argument's sake say this comparator threshold became this and this threshold became this, and this moved and this moved and so on. All right. Now, you do not know which threshold came from where. It could be that this threshold actually was this comparator's threshold, which is moved so much lower by due to offset, okay. But if you add the number of ones in the thermometer code, what happens? It does not matter, it appears as if you had a comparator array with these thresholds, correct. Is this clear? So, regardless of the amount of offset in these comparators, the characteristic will always be monotonic, correct. You understand. So, if the input increases, you cannot have a situation where the output code comes down. having a monotonic code, monotonic output is important because this is part of a feedback loop, otherwise the feedback loop basically will get confused. Okay. It is attempting to increase the output and then it finds that in spite of going in the same direction, the output actually decreases, and then it does not know whether it has to go in the same direction. I mean, how does negative feedback work? You compare the output to the input and tweak in a direction so as to reduce the error, right. If this the loop quantizer is non-monotonic, then you can expect trouble in the sense that you increase and then the output actually decreases contrary to your intuition, right. So, that makes the loop confused, you understand. So, adding up the number of ones in the thermometer code is a good way of eliminating non-monotonicity irrespective of the amount of offset. Of course, there you will still be stuck with DNL INL problems, correct, because these threshold spacings are not uniform. However, the requirements on offset can be greatly relaxed to get a certain, I mean to get a non-monotonic behavior. Earlier, a small amount of offset was enough to cause this kind of problem. Now, even though you get DNL and INL, you can rest assured that even if you have large amounts of offset, there will not be any non-monotonicity in the quantizer. Does it make sense? So, these comments kind of summarize whatever I had to say on flash converters as well as those aspects of a flash converter which are relevant to a delta sigma modulator loop, and then in the next class we will start with the other part of the puzzle, which is D to A conversion, right. So, we have made one half of the quantizer, which is the A to D converter. We need to make the, we need to understand what has to go into the D to A converter, which takes the output code of the flash and generates a current or a voltage, which is then fed back into the